Good day. Our topic for today that will be all about force, free body diagram, and the law of inertia. So force is defined as a push or a pull. Okay, it is measured by this instrument. Okay, and we call this one spring balance. So notice here you will see letter N. It stands for Newton. Okay, and it is the unit of force, while G or the gram, okay, it's the unit of mass. So if you want to know how much force is being exerted or needed to lift an object or to pull an object, you have to look at this N, the Newton. Next would be what's the unit of force. So I mentioned this a while ago, and it's coined after the name of the great Isaac Newton. So to have a better understanding of what Newton is. So let's have this situation here. So how much force do you need to turn on and off the switch? So it will take you 10 newtons to do that. And then how about opening a soft drink? Um, what's this? Cover. Okay, it will take you 20 newtons. And how about just simply standing? Okay, if you weigh around 50 kilograms or so, you will need around 500 newton. So we have here the different types of forces. We have gravity, oopsie, gravity, weight, friction, tension force, applied force, normal force, air resistance, and spring force. Okay, now let's start with the gravity. Okay, gravity is an attractive force between all objects that have mass. Let's say, for example, we have here the moon and the earth. They both have masses, so they are attracted from one another. Or let's just say us, like here on earth. This is the earth, and here we are. Okay, we both have mass. Okay, human. We both have mass. Forgive my drawing, by the way. So the Earth is attracted to us, while us is also attracted to Earth. Okay, there will be an additional explanation about this once we get to the law of acceleration and law of interaction. Okay, nevertheless, that's gravity. So let us distinguish first the weight and mass. Okay, this weight is related to gravity. Okay, when you say mass is the amount of matter in an object and does not change with location. Let's say, um, hypothetically, like for example, I have a rock and this rock have like 2 trillion atoms. Okay, okay, trillion atoms. Okay, just for this certain rock. Okay, so one here on Earth it has 2 trillion atoms, but once I put it in the moon, what do you think will happen? Okay, it will still have 2 trillion atoms. Okay, so meaning, okay, no matter where I go, maybe from Mars, Jupiter, Saturn, if it's possible, okay, the amount of matter, the number of atoms, or the number of molecules for a certain object will not change. Okay, so therefore, mass, okay, the mass, okay, is constant or fixed, even though you go to different places. Okay, but for weight, okay, it is the gravitational force on an object and changes with location. Weight is a force and a vector, and weight changes with height above. So you will understand it better if you know the formula of weight, because weight is mass times gravitational acceleration. of a certain place. So we have here mass. So that's why weight and mass is somewhat related, but they are not the same. Okay, and then we have this G. And we all know gravitational acceleration of the different places changes. Like just like for example here in Earth, it's 9.8 meter per second squared. Okay, and that's for Earth. And for Moon, okay, it changes. Like it's 1/6 of the gravitational acceleration of the Earth. So it's smaller. So that's why, okay, when you go to whatever your weight in here on Earth, and when you go to the moon, you will weigh lesser. Okay? You will weigh lesser.
Eureka! The story so far. All masses attract all other masses to a certain extent. The Earth, being a very large mass, exerts a very large force of attraction which is called the force of gravity. This pulls all objects towards the Earth at an acceleration of roughly 10 meters per second per second. The force of gravity acting on a mass of 100 grams is called 1 Newton. And now, weight versus mass. If anybody ever asks you what a Newton is, yes, you could give them an apple, or a couple of golf balls for that matter, or a small flashlight battery, because all of these have a mass of about 100 grams. And when the Earth pulls them down with an acceleration of 10 meters per second, we say that the force of gravity acting on them is 1 Newton, or that the apple, the 2 golf balls, and the flashlight battery are all pulled down to Earth by a force of 1 Newton. How many newtons are pulling you down to Earth? Well, the simplest way to measure a force is to use a Newton spring scale. If we hang the apple on it, we see that the Earth is pulling the apple down with a force of 1 Newton. And if we hang you on the spring scale, we see that the Earth is pulling you down with a force of, let's see, just about 600 newtons. So now we know how much you weigh. What you weigh merely means what force of gravity is pulling you down to Earth. That's all weight is, the force of gravity. Remember how keen physicists are on Latin words? Well, gravity comes from gravitas, which is simply Latin for weight. But you thought you were weighed in kilograms, didn't you? That's true in everyday life, but not in physics, which has to be very careful about these things. In physics, kilograms measure your mass on a balance, but your weight is always measured in newtons on a spring scale. You'll have noticed by now that you can usually work out the number of newtons by multiplying the kilograms by 10. 100 grams, or 1/10 of a kilogram, is about the same as 1 Newton, and 60 kilograms are about the same as 600 newtons. But if 1 kilogram is the equivalent of 10 newtons, why bother to make a distinction between a mass of 60 kilograms and a weight of 600 newtons if they both really come to the same thing? To find the answer to that, let's go to the moon. It doesn't feel as if you weigh so much here, does it? Let's see how many newtons are pulling you down on the moon. Only 100. Why is that? Because the moon is much smaller than the Earth, and therefore has much less mass. So its force of gravity is also much smaller, only 1/6 that of the Earth, in fact. This is why your weight on the moon is only 1/6 of your weight on Earth. What about your mass? On Earth, it was 60 kilograms. How much will it be on the moon? 60 kilograms. Exactly the same, of course. You don't get any smaller by going to the moon. You don't change. Only the force of gravity, and therefore your weight changes. That's the big difference between mass and weight. Wherever you go in the universe, your mass stays the same. Only your weight changes. So if you're not as slim as you'd like to be, don't eat so much. You should join the Mass Watchers Club. because you've got a mass problem. But if all you want to do is lose weight, go to the moon.
Second force, or second type of force, is applied force. Applied force is a force that is applied to an object by a person or another object. So let's have this example here. So this man has applied a certain force to this ball here. So basically that's it. So another, like if this is a box and this is you, if you are pushing the box, okay, you applied a certain force to that box. Okay. Next would be friction. Friction is a force that opposes the movement between two surfaces in contact. So just like this. Okay. So this boy moves in this direction, okay? And he is directly in contact with the ground, okay? And therefore, friction exists, okay? So again, friction will exist if there is movement, okay? And if there is movement and it has contacts, okay, with a certain surface, then there will be friction. So just like for example, if this is the box and then you're gonna move the box, okay? And by the way, this blue line is the ground, for example. And then you move that box, okay? When you move that box, there will be friction. Why? Because the box that is moving, and while it's moving, it's in direct contact with the ground, so there will be friction. Okay, so as a result, okay, he's in contact with the air, so he will have a friction. We're gonna call this friction air resistance. Okay, so we have to distinguish from this type of friction, because this one is in contact with the solid surface, from this type of friction, which is the air resistance. Okay.
Before the skydiver jumps, the floor of the plane provides a counterforce which balances the downward force of gravity, right up until the moment she steps out. Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity. When forces are balanced, the speed remains constant. That doesn't mean she's stopped falling, it means she's stopped accelerating. She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea. To slow down, the upward force needs to be greater than the downward force. When the parachute opens, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea. As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly.
the fourth type of force, that will be normal force. A normal force is a force exerted by an object that is perpendicular to the surface of the object. So what do I mean by that? So let's have this one. Okay, this is a table. Okay, and look at the table. It has a box. I mean, it's a glass. Okay, and the glass is weight. Okay, so this is the table. This is the table, and then here is the weight of the box. Okay, let me change the color of this. So here's the color. Okay, so look at they are now perpendicular. So this is the object and it's perpendicular to the surface. In this case, the surface is the table. So what exactly is the normal force? So let's have this one. Then if this is the glass, okay, and then this is the table. Now we all know that I mean the glass, why am I just mentioning box? That the glass is exerting a force downward because of its weight. But why is it that this glass isn't falling downward? Why is it isn't falling downward? It isn't falling because there is a force that somehow countered this weight, which is what we call the normal force. Without the normal force, box this box would fall down. Would fall down. Okay. Next type of force is spring force. Okay, it's the force exerted by a compressed or stretched spring upon any object that is attached to it. So I think when you were young, you have this kind of toy, and when you try to push this toy inside the box, you will feel that this box exerted a certain force upward, and that force is what we call the spring force. Next would be the tension force. A tension force is a pulling force exerted by an object when it's stretched. So just like this. Or let's say, for example, there's an elevator here, and there are cables. Okay, cables. Okay, and you are here. Let's say, for example, you are here. Okay, and we all know that we're gonna look at this elevator that um, it exerts certain force downwards because of its weight. Okay, the weight, it has weight. And why is it that the elevator is not falling down? Why is it that the elevator is not falling down? It is because it has a cable, and this cable exerted an upward force. Okay, an upward force just to counter the force of gravity or the weight. Okay, and that force is what we call tension force. The force exerted by the cable to this elevator is the tension force. Okay, now let's have practice exercise. So I have here a book on a table. So obviously, once um, being asked by like this, you always put weight. Okay, so you start with weight. Okay, it's the force going downward. What else? Why is it not falling down? Because it has normal force. Okay, and that normal force is being exerted upward. Okay, does it have applied force? Is there someone who is pushing this table? I mean, this book? No. How about friction force? Is this book moving? No. How about spring force? Is this attached by a spring? No. How about tension force? No, also because it isn't attached by a rope. And is it in contact with the air? No. So only this two, the weight and the normal force. Okay, next thing to do is we have to draw a free body diagram. Okay, what is really a free body diagram? Okay, I'll show it to you later. So you have to pick one object to analyze, draw a box to represent the object, draw an arrow to represent each box, each force acting on the object. Make sure that the arrow shows the direction and relative size of the force. So let's have this situation here. So again, how to draw a free body diagram, a book on a table. So we already identified the different forces acting on this book. So we have the weight and we have the normal force. So you have to draw first the weight. So from the center up to this point. Okay. Um, that's your weight. Okay. Now again, let's have this. The direction of the arrow will tell you the direction of the force. And then the length of the arrow will tell you how much force uh, it has. Let's say, for example, if it is shorter for a shorter arrow, it means shorter force or lesser force. If it is longer arrow, it means longer or greater force. Okay, so here this is now your weight, and this the green one that would be your normal force. So this is the weight and this is the normal force. So notice that when I draw the weight, it's from the center up to this one, and then when I draw the normal force from the center up, okay, and I label it Fn and I label it W per weight, and then you have also to notice that they have the same length. Okay, this is very important. So question, why do they have the same length? So in the given situation, a book on a table, so it's at rest, okay? So if your drawing is or has a longer weight, so if it's a longer weight, longer arrow, representation of weight, this book here would accelerate going downward, okay? Probably this table will gonna be broken, and then this book will going downward. But it's not happening because the book here is on top of a table and it's at rest. But what if this normal force is going out, I mean, it's longer than the weight? What if, let's say, I have this. If it's longer than the weight, what will happen? This books would levitate. It would fly, and and that's scary. We have to ask the help of Mr. Ed Kalawag for this one. Anyway, let's go to number 2. A skydiver is descending with a constant velocity. So the same thing, this man is on Earth, so it has its weight pulling him downward, and he is in contact with the air, so it has friction. How about, is there an applied force? No, because no one is pushing him. Number 2 is the friction force. No, because he is not contact with a solid surface. Spring force, he is not attached with spring. Same with tension, he is not attached to rope. And there's no normal force because he is not perpendicular to a certain surface. So we only have these two forces. So we have to put it here, weight and air resistance. So how to draw the free body diagram for this one? Okay, here, this is your weight. Okay, from the center up to this point. It's up to you how long it is. And then you have to draw the air resistance. The question is, um, which would be longer, the weight or the air resistance? Okay, so I'll put it label here. That's the weight, and this is the air resistance, F air. Now, why did I draw equal length of weight and air resistance because of this statement, constant velocity. Now, there will be an equal length, okay? Okay, if, okay, there is no acceleration happening. Okay. No acceleration. Why? Because the skydiver is moving in a constant velocity. So there is no acceleration. The skydiver didn't go faster or slower, it's just in a constant velocity. So therefore there is no acceleration. And also it's not changing its direction because it always goes downward. Now, so when I draw the free body diagram, the weight and the air resistance are equal, but they are in opposite direction. So in this case, look what happened. Okay, the same length, this without air resistance, so they are balanced. Okay, so again, the length of the arrow would be equal if the object is not accelerating. It would be totally different if this one. A rightward force is applied to a book in order to move it across a disk with a rightward acceleration. So the first force that we could imagine, that would be weight. Okay, second, normal force. Why is there normal force? Because the book is in contact with the table, it's a surface, okay, and it creates this is the book and this is the table. It is perpendicular. Next would be applied force. Why there is an applied force? Because this hand is pushing the table. And there's also friction force. Why is it there's a friction force? Because this book is moving, okay, rightward, and it's in contact with the solid surface. That's why there is a friction force. Does it have spring force? No. Tension? No. And tension? Okay. So that's it. Now, so how to draw the free body diagram for this one? Okay. Um, First, again, you have to identify the different forces acting in this situation. Okay. Next, you create a representation for weight. So just like this. Okay, this will be your weight. Next will be the normal force. Okay, from the center up to here. Okay. Now, again, what will be their length? Okay, their length would be equal but in opposite direction. Again, the same explanation with from the previous examples. If you will draw an arrow representing the weight longer than the normal force, then this book here probably would accelerate going downward. Okay, and if you're gonna draw an, an arrow representing the um, normal force, okay, longer than the weight, then this book would fly. But we are not observing that phenomena. So we could assume that the length of the weight and the length of the normal force is the same. Next would be applied force. So you applied a certain force just like this. So this will be your F, and then applied. Ooh, don't get your mind dirty. Okay, it's applied force, okay? So that's it. And then this one is moving, so we're gonna put the friction force, it's opposite in the applied force. So just like that. Oopsie. Okay. So the question is, why is it that the applied force is longer than the friction force? Okay. We all know that the object is moving rightward with an acceleration. So, if there is an acceleration, we could expect that the vector representation of the forces there must be longer and there must be shorter, meaning they must be there might be what we call the unbalanced force. And there's in this case the unbalanced force happen in the horizontal direction because the applied force is longer than the friction force. So here, there's an unbalanced force. How about here? No, there's no unbalanced force. But overall, yes, there's an unbalanced force because of this horizontal axis. The applied force is much longer than the friction force. Why do we do this kind of vector representation or free body diagram? Because of this statement. There is a rightward acceleration. Again, if there's a rightward acceleration, the arrow must be longer than its counterpart. Okay. Now, let's proceed to the law of inertia. So what is the law of inertia? The law of inertia states that if the forces are balanced, I'll explain this one later. Okay, object at rest stays at rest. An object in motion stays in motion, the same speed, and in the same direction. Okay, meaning, okay, both in these cases, there will be no acceleration. So let's go back. Okay, number one situation here. Okay, so here, let me erase this one. Okay, look that the weight and the normal force length are just the same, but they do have different direction. Okay, they do have different direction. So for example, if the normal force that just put numbers at 5 newtons and the weight is also 5 newtons but in opposite direction going downwards, so negative. So when you add the two, positive 5 plus negative 5, that will be 0 newtons. So there is no unbalanced force. In this case, this is what we call balanced force. Okay, so it follows the law of inertia. Okay, because forces here is balance. Okay, that is why in the law of inertia, at rest, the object at rest will remain at rest. So in this case, the table is at rest. It will remain at rest forever and ever because the forces here are balanced. Okay, here for number two, okay, we have this situation here. Okay, and the same with number one, forces here are balanced. Okay, then the weight and the air resistance are balanced. So for example, if this is 5 Newton and this is negative 5 Newton, so they cancel out, that's 0 Newton. So forces here are balanced. And if forces are balanced, then we could say that it follows the law of inertia. And that second statement of law of inertia is that an object in motion will remain in motion in the same speed and in the same direction forever and ever. So if this man here it moves in constant velocity, meaning constant speed and the same direction forever and ever. Why? Because it experiences a balance force. Okay, it experiences a balance force. Okay. And the story would be different in this case. Okay, why? Because there is now an introduction of unbalanced force. In this case, the unbalanced force is in the horizontal line between, between the applied force. Let me erase this one. The applied force, ooh, and the friction. Okay, so if you observe, the applied force is much longer than the friction there. So there is an unbalanced force. And this unbalanced force is um, the one who would explain what would happen if there is an unbalanced force. That would be the law of acceleration. It will be no longer the law of inertia. So I hope this one is clear. The law of acceleration and the third law of motion, which is the law of interaction, would be discussed in the next video. But for now, let's go back to the law of inertia. Again, I hope this one is clear. When forces are balanced, meaning the net force is zero, okay, an object at rest will remain at rest. An object in motion, meaning if it's moving, okay, will remain moving with the same speed in the same direction forever and ever. So we have here the last and final question. Does an object need a force to continue moving? So the answer is no, because uh, once it moves, it will move forever and ever, okay, in the same speed and in the same direction. But why do we observe different thing here on Earth? Because, okay, for example, if this is the ball and this is the ground, if you push the ball and it will move to a certain point, it will continue moving but eventually stop. Why does it stop? Because of the force of friction. But without the force of friction, if you're gonna get rid of the friction force, then this ball will move forever and ever in the same direction and in the same speed. Okay, thank you and goodbye.